I have an 8-channel relay board that uses 5 volts to power the relays as well as 5 volts for the control inputs. And having up to 8 control pins, it would be nice if I could use an 8-pin GPIO expander with I2C to minimize connections. So I want to try using the GPIO expander with an Arduino Uno running at 5 volts to control the inputs on the relay board. But since not everything runs at 5 volts, I'm also wondering, can I still power this at 5 volts because it does need that for the relays, but control it from a 3.3 volt system? So even using the Uno, I can run the GPIO expander by powering it from 3.3, and then the I2C gets pulled up on board to 3.3 and then has 3.3 volt output controls. And finally, if I had a real 3.3 volt system like an ESP8266, can that directly drive these inputs? So to investigate the ability to run at 3.3 volts, I'm going to want to characterize the switching thresholds of these inputs and compare against the output high and low logic levels of the GPIO expander as well as an ESP8266, and then hook it all up and see what happens. The main header has ground and VCC, which is 5 volts, and then 8 control inputs that are active low. So when these are high, it's off, and when it goes to ground, it's on. The coil is 5 volts DC operated, and the contacts are rated 10 amps, and you can go up to 30 volts DC at 10 amps, or up to 250 volts AC at 10 amps. Each relay has 3 screw terminal contacts, so you have single pole double throw. The common would be in the center, normally closed is on the right, and normally open is on the left. So the common switches between this contact or this contact when you turn the relay off and on. There's a red indicator LED to show if the channel is on or off. There's an opto isolator, and then there's a transistor to drive the relay and a protection diode across the coil. Although this is an opto isolated input control, by default there's a jumper installed that shares the 5 volts of this input control circuit with the 5 volts powering the relay, so it's not fully isolated by default. We can take the jumper off, and now these V-in pins only go to the optocoupler circuit, and this other pin right here goes to the relays. So we would give an isolated 5 volt supply here and a separate 5 volt supply for the logic side. Now it's isolated. This VCC pin right here on the bottom side routes over to the VCC pin on that jumper and then continues on to all the optocoupler circuits. So with the jumper on, the same 5 volt VCC goes on and powers the relay. But with the jumper off, all we have is VCC going to the digital side, and we give 5 volts directly to the relay here. Here's the schematic of one channel on the relay board. We have ground, which is common with the relay power supply. We have VCC, which I'm going to call plus V, and then we have this jumper up here between the 5 volts on the relay and that VCC plus V. So if the jumper's installed, the 5 volts on the relay driver side gets shared with the VCC pin powering this logic side. If the jumper's removed, this header's VCC pin just goes to this digital side, and we would have to apply 5 volts right here just to do the relay side, and ground here. So if we are going to use 2 different 5 volt supplies for isolation, if we really want to be fully isolated, we're not going to tie this digital side ground over here. What we're doing is applying a ground or a plus V on the control input. So in an isolated setup, you could think of it like this. If you had another circuit that's driving an LED where the anode and resistor are on VCC, and you turn it on by setting an output low, over here we have a resistor and 2 LEDs and a cathode that we could connect to drive low and power the isolated plus V rail, which goes nowhere else with the jumper off from this system. At least that's a general concept. To turn on the relay The LED inside the opto isolator turns on the transistor. That brings 5 volts through a base resistor to turn on a relay driving transistor and turn on the relay. When this input is brought high enough toward the +5, there's not enough voltage drop across these LEDs to turn on the opto isolator, so the relay goes off. When it's off, the relay output screw terminal contacts are shorted between the common and normally closed. When you turn the relay on, the common switches over to the normally open. The LED in the opto isolator has a forward voltage of around 1.1 or 1.2 volts across it when it's on, and this red LED has about 1.85 volts across it when it's fully on. So it's around 3 volts dropped across these two LEDs, and with 5 volts, that gives 2 volts across this 1K resistor. So 2 volts divided by 1K is approximately 2 milliamps of drive current that this is designed for. If we want to actually change this from +5 to something else, like we want to try and drive this from a 3.3 volt system, we have to make sure we still have enough to get a 3 volt total drop across these two LEDs, and then whatever's left, if it's a 3.3 volt system, we'll have 0.3 volts across a 1K resistor, and that gives us a lot less current to drive all of this. So on the workbench, it may work to use 3.3 volts right here on this pin. For sure, if we're only using 3.3, we definitely want to remove this jumper and still drive the relays from 5 volts to reliably actuate the mechanical switches with the coil. So my test setup is going to be keeping the jumper on, giving 5 volts to the whole board, so the relay gets 5 volts. This digital circuit gets 5 volts to work with, but I want to try having an input that goes both between 0 and 5 volts and 0 and 3.3 volts. Is 3.3 volts enough to keep this off? Ground is on, 3.3 and 5, hopefully both will turn it off. If I put 3.3 volts here to turn this off, what we have across the resistor and two LEDs, 5 volts minus 3.3 is 1.7 across all of this. Since we need about 3 volts to turn on these LEDs, a 3.3 volt input should turn this off. So that's what I'm going to first characterize. How does this all look as I change my input voltage from 0 to 5 volts? And what happens in between at 3.3? So here I have 74 milliamps turning on this relay. So if I add another relay, I should get about twice as much current, about 150 milliamps. So there's 147 milliamps, and I've got the second relay now on. If I add a third, I should get another 74 something milliamps. So it's close to 215. And if I add the fourth relay, that should be somewhere around 280 milliamps plus. It's hard to push all 4 buttons. This green light should come on when I get that fourth relay on. All 4 on, 280, 81 milliamps. Now I've got a big pile of connections here. There's 2 different lab power supplies, both 5 volts. I have a fixed one going in to power the coils as well as the digital power side of the optocoupler circuit. And then I have a variable 5 volt supply that I'm going to use on the actual input number 6, to go between 5 volts and ground and see when this switch is off and on and how it looks in between. So here's the exact voltage that I'm applying on my control input, and this is the current that's going to be going through that input pin. So the current going through the optocoupler LED, the resistor, and the indicator LED. So the jumper is on, therefore I'm sharing one 5 volt input to drive the relay and power this optocoupler circuit. Then I'm putting another separate variable power supply right here and controlling this from 5 to ground, and I'm measuring the current through here. So at 5 volts, as expected, the system is off. You may or may not be able to see when the LED comes on, and because it's off, we have 0 current draw. This will be in milliamps. Nothing's going to happen really between 5 volts and 3.3, but 3.3 is a point of interest, so I'm going to skip right down to 3.3. So now I want to see when this actually starts to switch on as I lower the voltage, and I want to see when I start getting a current flow, which will occur before it actually turns on, so we can see that we're getting into conduction. When I'm around 2.6 volts in, I'm getting about 4 microamps of current. If I go down to 2.35 volts, I get around 50 microamps of current, and I can start to see the red LED glow a bit. At 1.95 volts, the red LED is brighter again, and it just switched on while I was talking. So this is the switch on voltage, and we have 250 microamps of current allowing this to switch on. So then as I go all the way to ground, now it's close to ground, I have 1.9 milliamps through the circuit turning on the LED. It's as bright as it's going to get. Relay's on solid. So while increasing, I get back to around 1.95. It's still on. Close to 2 volts, it's still on. So while increasing the voltage, it switched off again when it got around 2 volts or maybe slightly more. So I guess it's around the same, turning it off or on. Somewhere close to 2 volts is the switching threshold. I have 2 schematics for the GPIO expander controlling the relays, since I'm going to try with an Uno as well as an ESP8266 with Node MCU. It's pretty much the same sketch. So looking at the Arduino Uno, the GPIO expander has 4 outputs controlling the relay and 4 inputs for buttons going to ground, and then the interrupt output is going to digital 2 for an interrupt input on the Uno. We have I2C going off to the GPIO expander, and whatever voltage we are giving this, that's the voltage the I2C is going to work at with the onboard pull-ups. So we have a common ground between everything. We are giving 5 volts onto the breadboard, and we're using it to power this LED on the relay output, and we're using 5 volts in ground to power the relay and the optocoupler sections of the relay board. And for the GPIO expander, the VCC is going to a switch, and I can change if I want to run it at 5 volts or at 3.3 volts. So by flipping a switch, suddenly these GPIOs are working at 0 and 5 or 0 and 3.3 volts, and the functionality is the same. So each button directly influences one relay. For the Node MCU ESP8266 3.3 volt system using a GPIO expander, it's essentially the same as the Arduino Uno setup, except the GPIO expander is fixed at 3.3 volts. So the I2C default pins are being used. I'm using digital 4 as my interrupt input. Otherwise, I have the same 4 buttons, 4 relays, and 1 light in this example. So this will run the same sketch as the Uno to control the buttons and relays. The only difference is which pin is an interrupt pin between those 2 designs. To control the PCF8574, this time I'm going to use this library because it has routines to do specific things, like reading or writing the entire port or just 1 pin at a time, or toggling whatever the last state was. Otherwise, we'd have to add all kinds of features like this directly in our sketch to make sure if we only want to change 1 pin, we're not messing up the other 7. The sketch I came up with, I'm using the interrupt output pin from the GPIO expander to tell me when a button has been pressed. So whichever board I'm using, this will be the interrupt input. If I want to read in the buttons, I have this button register variable, and as an interrupt flag, I have a button pressed variable, and it will be true or false depending if we've had an interrupt signifying a button has been pressed. If we had an interrupt triggered, so a button has been pressed, I'm only controlling the first 2 buttons by interrupt. I'm just showing different ways to read in the inputs. So if there's been a button press at all, we check, is it the first or the second button? And if so, toggle the state of the associated relay, and then clear the interrupt flag because we already handled it. Aside from if there was or wasn't an interrupt, we are going to manually check the other 2 buttons. So there's 2 ways. First, I can just read in all the GPIO pins and then write specifically to the relay pin with the value of the button. So if the button's being pressed, it's being pulled to ground, which gives us a low in, and we're sending that low out to the relay. So with a button being pressed, we want the relay on, and sending a low out turns on the relay. For the final relay, we're just going to use the single command to write that relay pin with whatever we immediately read in real time on this specific GPIO expander pin, button 3. So since I just read this whole button register in, I could have also just said right here, write GPIO 7 relay, and then bit read button register, and 3 because it's pin 3. So it's just different ways to do the same thing. I have everything hooked up now. I have a lab supply giving me 5 volts and 12 volts. I have the Uno right here, and the PCF8574 is back here. And then I have 4 push buttons right here. So I'm using these top 4 relays. And I have various indicator lights that I found throughout my collection. I wanted to show how much current I'm using every time I add another relay. Ooh, I got a new subscriber. I know I'm getting some losses in all this wiring when I have all the relays on, especially where I'm drawing a couple hundred milliamps. So the current consumption in a proper wired circuit would be a little bit higher than what we're going to see here. I'm going to measure it, and in order to prevent further losses, I found it's best if I just hold these test leads on directly. The 4 buttons are set up so that buttons 0 and 1, every time I press, it will toggle the respective light. Buttons 2 and 3 are reflected in real time on those 2 lights. So if I push button 0, the first light should come on. And I'm drawing 60 milliamps. I'd probably be drawing around 70 if I had better wiring. So if I press it again, it will toggle off. The next button should toggle the next light. I can turn both on independently, on and off. So now when I press and release button 2, the green light should go on and off as I press or release. Same with the next one for the red light. And just dimming everything a bit. Here's the lights, more visible. So just tracing through the circuit that controls the relay. To turn the relay off, we give it 5 volts. To turn it on, we give it ground. But what if we want to drive this from a 3.3 volt circuit? Alright, so this is getting a bit squirrely at this point. Notice the subscribe counter only shows 1 digit. So I'm powering the GPIO expander from the 3.3 volt side of this Uno, and that's really all this Uno is doing now, aside from giving a place to tie in common grounds. So this is running at 3.3. It's going to give 3.3 control signals to the relay, and the I2C and common ground are now coming from this node MCU, as well as the interrupt pin. It's running the same code I had in the Uno, except I changed what pin I'm using for interrupts. But since it is still using I2C, I still kept the I2C for this Nixie driver setup, and one of these 2 GPIO expanders here have the same address as the one I'm really talking to control the relays. So both are listening in at the same time, and we can have some fun with that. Now as I control the 4 input switches and drive the relays, these 2 digits are going to interpret what's happening here. So let's see. I'll turn on some lights. Okay. Okay, so I get an 8 on the Nixie, as well as getting this green light. Turn on the red light, I get a 4 on the Nixie. Turn on both, I get a 0 on the Nixie because there's different binary values going out. Well, that's interesting, but it's not what I'm trying to accomplish right now. So with a 3.3 volt circuit, basically I'm getting my 3.26 volts out of my 3.3 volt circuit. So 3.26 volts is high enough to turn off the relay. When we turn it on, of course, we get our good ground and a 7 on the subscribe counter. Turn it off, 3.26 volts, and it's solidly off. But if we wanted to drive these inputs from something other than a 3.3 volt PCF8574, now I'm using a node MCU with an ESP8266, all 3.3 volts, with a sketch that turns an output, digital 3, on and off at 3-second intervals. And the GPIO is going straight to the input on the relay. The red LED is going on and off. There's clicking. Now it's off because it's 3.3 volts. Now it's on because it's close to ground. So we don't have any trouble getting a 3.3 volt logic high out of this node MCU ESP8266. The datasheet said an ESP8266 logic high output could go down as low as something like 2.6 volts. So let's observe that. I'm going to take that GPIO and ground. I have a 300 ohm resistor, so on a 3.3 volt signal, that should try to draw about 11 milliamps. Now the output low is closer to ground, 0.05 volts, and the logic high has sagged 2.9 volts instead of 3.3. So the harder we load down the GPIO, the lower the output voltage will be. So I suppose this could go down to 2.6 when we draw the most current we're allowed to on the port. But it looks like for the minimal current just to turn on this optocoupler and indicator light, we're getting a good 3.3 volts. The reason I wanted to test this with an actual load circuit is because in the ESP8266 datasheet, it just had that number, that it could drop as low as 2.6 volts with a logic high out. There was no graph showing what you would get at different load currents. So I couldn't look up 2 milliamps and see how much output voltage I should expect. The PCF8574 datasheet had a graph, so I could tell I'm going to get close to 3.3 volts with this kind of load, but this one I wanted to test myself. Looking at the summary of these various control methods, to turn the relay off, we need a logic high input, and we have found the relay definitely is off if we have 2.7 volts or greater. Using the PCF8574 at 5 volts, our logic high is about 5 volts, so that's okay. At 3.3 volts, we get about 3.3 volts, and that's okay. Using the ESP8266 with a 3.3 volt logic high out, we can expect it to be as low as 2.64 volts, which is very marginal here. With this relay circuit only drawing 2 milliamps out of the GPIO pin, we do see closer to 3.3 volts. So it'll work, but in a production design, maybe we would want more margin, even if we know we're not going to draw more than this much current, because the datasheet did not clearly say what condition on the I/O load is going to result in what actual voltage. We just empirically tested this, but maybe also over temperature. We have just a 2 milliamp load, but maybe at 40 degrees Celsius, this 3.3 that we are seeing is going to go down toward the minimum. So we don't know, but for testing on the bench, it's okay. So to turn the relay on, we need a logic low input, and we have seen the relay turns on anywhere between 2 volts down toward 0. Closer to 0 is better. So the PCF8574, whether it's 5 or 3.3 volts, we're expecting our logic low to be less than 0.1 volts, which is good. With the ESP8266 logic low output, the datasheet says it should be less than 0.3 volts, which should also be good. So all of these cases can drive this relay. So that's how these 5-volt controlled opto-isolated relay modules work, and in this case it looks like whether running at 3.3 or 5 volts can drive it just fine.